This is Ashwin here. So we are going to see about spanning tree in this video lecture. So what is a spanning tree? So we are going through the concepts of graphs, and tree means it does not contain a cycle. That's what we have defined tree in terms of graph definitions, right? Spanning tree is a special subgraph of the main graph. So let us define the graph V comma E, and then these are the two conditions that the spanning tree should satisfy. First condition is that it should contain all the vertices of V comma E. So now if you have a graph, the spanning tree should have all the vertices. Now next condition is that it contains only certain edges from G such that there is no cycle. That means there is no cycle in the spanning tree, but it should contain all the vertices, right? And there should be n minus 1 edges, because if there is no cycle, it satisfies the tree condition. If it satisfies the tree condition, the number of edges should be equal to n minus 1. So this is an example of a graph. This is a weighted graph because each of the edge has some weights assigned to it. So this is a new case that we are seeing here. So this is something which is weighted. Let me give a spanning tree example for this. So let me define spanning tree ST1 as like this. First condition, it should have all the vertices, right? So let me write all the vertices here. A, which is B, which is C, which is D, and which is E. So all the vertices are there. First condition is satisfied. Now there should be no cycle. So let me randomly draw the edges from this. So there is an edge from this to this. There is an edge from this to this. There is an edge here. And there is an edge here. So there are 5 A, B, C, D, E. There are 5 vertices. And there should be only n minus 1 edges, 4 edges, such that there is no cycle. This satisfies the condition. Now you will also have to put the weights on this 2, 2, 3, and then 4. So this spanning tree's total weight will be the addition of the edges, right? 2 plus 2, which is 4 plus 4 is 8. 11 is the cost. Okay, or else I'll write it as 11, right? Cost for traversing the spanning tree. Let me draw one more example. Spanning tree 2. So the first condition is that it should have all the vertices. Right? It should contain all the vertices. Now, if I can minimize the possibility of this minimum cost spanning tree, that is a new problem in graphs. So, which we have two algorithms called Kruskal's algorithm and Prim's algorithm that we'll be discussing. But if at all by seeing this, if we can minimize the possibility, like I can say that this is obviously lesser. So, I am drawing this edge here, right? And then if I see, I can draw by means of just looking, and then there is one more edge that needs to be added to connect to C, right? We can add this edge. Now see the cost of this spanning tree, which is 2 here, again 2 here, 3 here, and 1. So the cost of this spanning tree will be equals to 2 plus 2, which is 4, plus 1, which is 5, plus 3, which is 8. So minimum cost spanning tree. So there are algorithms to find out the minimum cost. Since this is a simple small graph, we were able to figure it out ourselves, but then there are more proper algorithmic ways to find out the minimum cost spanning tree. Thank you.